you. So I am Chetan and he is Vishal. We are both open source lovers, Python developers, and we like to share our learnings across. So this is one of our learnings that we had recently. So how does a typical day of a Python programmer looks like? He faces a memory error exception in the morning for his breakfast. During lunch, he is feeling that Python memory of the program that is written, the memory that's trying to use is quite bloating. It's going on and on. It doesn't do much about it. And during the evening, he feels that there is no more RAM now with which I can extend my laptop or my operating system and get my program going. So at night, he's really bewildered, like confused. What next I can do, or how can I scale my application? So let's look at some of the basics here. Python memory management. So Python memory allocator looks something like that. So at the bottom we have the OS memory manager, which allocates the memory. Then we have a general purpose allocator, malloc, cloc. On top of that, we have the Python raw memory allocator, which actually allocates the private heap to any program that's running. And in general, we have the Python object allocator. So Python object allocators allocates memories based on the data type that it needs to attend to. So let's say we have an integer or you have a string data type, then the object allocated depends on the data type. So if you actually go ahead and look at the source, it looks you can view it under objects of malloc.c. We actually have the source code open with us. After the talk, if anybody wants to go through it, we can do that as well. So as we know, Python, everything is an object. Your int, your string, it doesn't matter. Everything is an object. So what a typical object is attributed to? An object will have an runtime object identity. It has a value. It has a type. So let's say I say a type is a variable a is equal to 42. So 42 is the value it is associated with, and the value is 42, and the type of the data type is int. So the famous things about mutable and immutable objects. So immutable objects, we have primitives versus constraints. So numbers and strings are immutable, and the mutable objects are basically lists or dictionaries. So let's go ahead and understand more how these memories are allocated and what are typical problems that we face with this. So it's another graphical representation of the same slide that we had in the previous thing. An object will have a typical type ID. It's a runtime ID. When we have identity, we have a value, and the value could be of type mutable or immutable. So let me call upon Vishal to understand the actual memory problems that we face.
Thank you, Chetan, and hi everyone. Am I audible? Am I audible?
Thank you.
Yeah. So let's dissect the problems that Python VM has one by one. So first problem I'm going to talk about, it's an optimization that Python VM has. It's called interning. So the Python VM allocator reallocates few objects. First of all, the interesting thing about Python VM is that it manages objects which are less than 256 bytes. If object size is bigger than that, all the allocation and reallocation is handled by the system allocator. So object sizes of less than 256 bytes are handled by Python VM. The interning of object, it is meant for avoiding the allocation and reallocation overhead that is associated with these objects. So say integers from range 1 to 256, they are always interned. So no matter you are going to use them in your application or not, they will always be ref counted by more than 1. They will never be reallocated from the memory. So that is fine. But if we keep on creating objects and these objects are interned, then in that case, if your application doesn't use those objects later, then you will end up consuming your memory just like that. And this memory is not available to system or other applications. So as an optimization, it can become a bottleneck for your application itself and the system as a whole. Let's see it with an example. So in this example, we have created a range of about 1 million objects. These objects are integers. Then I delete the reference to the object, and let's see what is the pattern of memory. So here we see I have used a tool called memory profiler, which gives you line by line memory consumption of a Python application. So look at line number 5. Here we have allocated about 15 MB of RAM to represent those 10 million integers. But even after I delete the reference to variable L, the memory is still claimed by the application. It's not freed up for other applications in the system. So this memory is still held by the Python VM. It's not freed. So this is the interning and optimization that turned out to be a problem. See, one more thing, that these problems you might hit only for applications that runs for days or months. So if you write a highly scalable, highly performance servers in Python, like a web server, so in those cases you might start hitting the problems that Chetan discussed in the beginning. Let's have a look at problem number 2. This is about the Python object behavior. So as we all know that Python VM works on ref counting and just like Java. So just have a look on the left hand side. We have 2 assignment statements, and we have assigned a number to two variables a and b. Internally, we will just bump up the ref count of object 42. We will not create object a and b, rather we will create 2 aliases. Look at right hand side. So we have 2 lists, both are exactly same, both have same elements, but in this case we create 2 different objects. So this is an important difference. So if you have objects that are mutable, in that case they all will have a different memory for each of them. But if you have immutable objects like numbers, we will just bump up the ref count of the original object and we create aliases. So just have a look at one example. So here we have variable a and b, just we have assigned a number 1, and we are printing identity of variable a and b as Chetan talked about it in the beginning. Identity of an object in CPython VM is implemented as the address of the object itself. So it's a runtime address, and we are just printing the ref count of these objects and seeing how does the pattern look like. So as we saw, since 1 is a constant value, so a and b both have the same address. So a and b just share the same reference. Ref count of 1 is incremented every time we do an assignment. As we do the deletion, just last but one line, deletion of object C, ref count is incremented again. So interesting thing is, how come ref count of 1 is so high? How come it is 370? Any clue? Okay, as I talked about interning. So objects like 1 are, first of all, they are very common. So there would be many pre-existing references in the Python VM itself, or else the Python VM would itself have created multiple references to object 1, since it's used so many times in the VM itself.
Vishal, did you try 0 by any chance?
Not yet. Okay. Let's have a look at mutable object. So we have here 2 lists and 2 tuples. Both of them have same value. I have printed identity of list, identity of the tuples, and let's have a look at the output. So both the lists have same value, they have same objects, but they are 2 separate objects represented in the VM. So memory for both the objects are allocated separately, unlike numbers or strings. Then look at lists, tuples. So as we all know that tuple is an immutable object. I mean, we cannot change the content of a tuple, but implementation wise they behave as a mutable object. So although both the tuples have same elements, they have different addresses. And objects like tuples, list, dictionaries, they are termed as containers, since they keep references to other objects. So just have a look at the last lines of code. So here we are changing the value of the referencee, that is the a and b. So since tuples have the address of a and b, not the value of a and b, so addresses of tuple 1 and 2 will not change at all. So in the last line of the output, T1 and T2 still remain the same. So Now we understand that for mutable objects, we have separate memory for each object, each of them. So if you create two lists, so you have two copies of the list, although they have same values. For immutable objects, memory is shared, and we just bump up the ref count, and most of the immutable objects are interned. Third problem is about the data sizes that we have in Python. So I mostly code in C and sometime in Python. So in C we have data sizes which are very efficient. It's mostly work on the system level, but in Python object sizes differ a lot. So size of an object doesn't matter if you have a small application, but if you write a highly scalable application which creates millions of objects at a particular point of time, that these problems will start to hit the performance or the scalability of the application. So I just had a look at the definition of, say, string in Python VM. So if you see that other than the value, there are so many metadata that we have to keep with each object. So these metadata itself has an overhead for each object allocation. Let's have a look at how does the sizes of these objects look like. So as a sample, I just took few of the strings, some numbers, and some containers like list and dictionaries. So the first string is just a 10-byte string, which is represented by 31 bytes in Python VM. A 64-bit integer, which could have taken just 8 bytes in C, it's taking 22 bytes to get represented in Python VM. And empty string itself takes 21 bytes. More interestingly, look at the containers. So an empty container is 32 byte, and the list, and a list with 3 elements, that is the size of the empty list plus 3 references, that is 4 3s are 12. So 44 bytes to represent a list of 3 integers. And dictionaries are pretty expensive. So an empty dictionary itself takes 136 bytes. So why these sizes are so big? So first thing is, see, these objects like containers, like dictionaries, for example, they are very efficient data structures. So to achieve that optimal lookup time, we could create many supporting data structures like a tree or a hash table. So the overhead of those metadata structure is also accounted for when we create a dictionary anytime. That's why the size is so big. So observations so far, we have learned about the mutability and immutability of the objects. Now we know that objects are not cheap in Python VM. So if your application is creating millions of lists or dictionaries at a time, be cautious, be judicious when you want to use them or not. And immutable objects are interned, as we know. Fourth problem is pretty, it's famous. So Python VM has a garbage collector, which is little special. So special as in it is based on only 2 mechanism: ref counting, that is a reference counting of an object. So each object has a ref count field in it, in its structure. If the ref count becomes 0, the object is deallocated, the memory is freed. And the other thing is called reference cycle. So instead of finding out which objects are reachable, Python VM finds out which objects are unreachable. So ref cycles are a cycle of objects where each objects keep a reference of each other. So in that case, these ref cycles are formed by your application, and since ref cycles are based on references, simple data types like integers or a string are not tracked, since they cannot have references of other objects. So garbage collector only tracks containers, that is lists, sets, tuples, dictionaries, and such objects. Then implementation wise, if you have a look at the garbage collector, it has 3 generations of each object. So it is generation 0, 1, and 2. So the age of an object is formed by the mark and sweep algorithm that VM has. So every time an object is found, it is marked at young generation. If it's found in the next iteration, it is elevated to next generation. So every time an object survives a sweep, it is moved to next generation. So old objects are kept for the longer time, young objects are freed as early as possible. Garbage collection is an optional feature. If you believe that your application doesn't leak any memory and your application is perfect code, then you can disable it, and you can interact with garbage collector using the GC module in Python VM. Let's have a look at the problems that collector has. So the only problem that we found has been the reference cycles. So since cycles are formed when object keeps references to each other, now assume that if your object has a finalizer, that is the del method. So these finalizers are called whenever the object ref count becomes 0, but application, if the class has a finalizer method, Python VM has no idea of the ordering of the call. So if it doesn't know the order in which the object has to be freed, these objects are left as it is. So these cycles are never collected, and the memory allocated for the objects in those cycles just remains there. So say if your application keeps on creating such cycles and it runs for say days, you would have a lot of memory which is unclaimed and unusable by the Python VM. So this is the fourth problem. So just have a look at the cycle we have. So we just created a 10 million objects, and to create the cycle, it's very easy. List can have a reference to itself. So in this case, we have a cycle. So even if you delete the reference to L, in that case, there is no way we can reach the cycle now. So the memory for this object, it remains unclaimed. Fifth problem is memory leaks in your extension. So as Chetan told, that Python VM manages its own heap, and this memory is not shared with the system. So if you have extensions which are written in C and C++, memory problems of your extension have to be handled separately. So Python VM would have no idea how your extensions are allocating or reallocating the memory. So for applications written in C, we can use Valgrind and Massive tool to find out if they have memory leaks or not. So summary wise, problems are interning, object sizes, object types, then reference cycles, and memory leaks in the extensions. So now we have an understanding of the problems that Python VM has. So we found few tools which could be helpful for developers to find and fix the problems. So first tool is memory profiler. We saw it in all the examples so far. It's the easiest tool I found it to use to understand the memory allocation pattern line by line in the application. It is based on PS tool. I believe it's available only for Linux, and all of our examples are based on Ubuntu. So it just gives you the VM size of your application periodically. That's all in memory profiler. So here I think we have already seen this example. The other tool we found very useful was Objgraph. So Objgraph is a pretty extensive tool, and it is based on the garbage collector that Python VM has. Since garbage collection is based on objects, objects have references to other objects. So Objgraph can create graph of all the objects that Python VM is tracking. So with this tool, you can find out memory leaks, ref counting problems, and ref cycles in your applications. One example I have. So we have to import the Objgraph module. I created a list of 2 objects and created a ref cycle, then a dictionary which just references the list. And I called Objgraph to show all the references that are from D. So all the references that are outgoing from D. So it will look like this. So dictionary is the D. It has only one item, that is key, and the L is the value. So left hand side is the key. List has 3 items, 2 integers and a self reference. So integers are 1 and 0, and a reference to itself. So it's very easy to find out ref cycle using Objgraph. Then there is another tool, it's web-based, it's called Pythontutor. It's very similar to Objgraph, but looks more intuitive. Actually, it's not just for finding problems. If you want to represent your application as a graph, you can use Pythontutor.
So hearing the talks slides given by Vishal, we feel it's very pessimistic side of Python. Should not code at all in Python, but yeah, there is some optimism as well. So as far as possible, as like based on our experience, we feel it's best to use 64-bit Python VMs. And we should have an idea of what Python objects that you are creating in what order, because we saw through Vishal's slide. Because if the objects are not created in a proper manner and not deallocated in an appropriate way, they remain unclaimed. Use xrange. Those kind of optimizations are pretty useful. Force the garbage collector, delete data, use weak references as much as possible. Here's an example of avoiding creating reference cycles, as Vishal told, the problems associated with reference cycles. So they can't be, there's nothing that Python can do there. You need to go ahead and manually delete, explicitly break those cycles yourself. Garbage collector is another good model which is provided by Python. You need to schedule frequent garbage collection terminologies there. You could do a del gc.garbage and do much kind of things. And try using slots. Slots is another optimization wherein a class member is assigned. So if you have a class ABC, under that you could create __ slots __ equal to a list or a dictionary. That's a very good optimization. So it doesn't get involved in the dynamic memory allocation at all. So here are some of the good best practices and lessons that we have come across during our own investigation. Here are some of the references that we have used, Pythontutor being one of them. Objgraph and Pythontutor are some of the tools that we would like to recommend for detecting such Python memory problems. I think that's it. Thank you.